Okay, we're going to do additional problem number 2. And this problem deals with rocks being ejected out of volcanoes on Mars. So our first job in this problem is to distill the information that you're given into what's useful. And so one of the things that's important about this one is that in here we're told that we can look up the height of Martian volcanoes and determine the distance rocks from a volcano hit the ground from pictures. You don't actually have to do that though. Right? So it turns out that in this problem we're given a very important piece of information. Right? And it's in that last sentence. If you assume the rocks farthest from the volcano are ejected at an angle of 45 degrees, we want the magnitude of the rock's velocity as a function of its distance from the volcano and the height of the volcano for the rocks furthest from the volcano. So, and the height of the volcano for rocks furthest from the volcano. And so let's draw a picture here and get a sense for what we're looking at. So our volcano kind of does this. It does this. And we know that it sort of spews stuff out, kind of goes all over the place. But we're told that the rocks that go farthest away from the volcano happen at an angle of, or come out, have initial velocity that's 45 degrees from the horizontal. Now I don't know what it is, but when they come out at that angle, they have some initial velocity, v0. Put the vector on there. Okay. So we don't know what it is, but the point of this is that, well, we're going to assume that it's largest at 45 degrees here. And so this is basically sort of a disguised kinematics problem. And it looks, if we want to visualize this a little simpler, here's what we have. Okay, we have a rock that's being ejected with some initial velocity, 45 degrees here, and it starts at some height above the ground, h, and it travels some distance. And so the trajectory is going to look something like this. Boop, 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 boop. Goes down, and then it hits the ground, which I'm going to call y is equal to 0. But it travels some distance, x final. And that's really all that we need to know here. Because even though the acceleration, so we're going to use gm is 0.4 g, so that's the acceleration due to gravity on Mars. It's the same type of problem that we've been dealing with before. It's a constant acceleration problem. And so what I'm going to do here, and again, this is a little tricky, it's not quite clear exactly what to do. Let's write down our kinematics expression. Let me define my coordinate axes. This is y and this is x. All right. I'll set y is equal to 0 here. And I'm going to set x is equal to 0 here. So my position, my height, is going to be my initial height plus v0 in the y direction times the time plus 1/2 ay t squared. And a couple things that we need to keep in mind. First of all, this, well, we have to use geometry to find that. So v0y is going to be the magnitude v0 times the sine of 45 degrees, which is √2/2 v0. It turns out that actually, since we're doing it, that also, by the way, v0x is going to be v0 cosine 45 degrees, which is also √2/2 v0. All right, so that's important. And what we can do in this with this expression is we can say, well, if I want to know the time it takes to get from here to here, well, that happens when the height is equal to 0. When the height goes to 0. So that's going to be my initial height plus √2/2 V0 times t plus negative, because the acceleration due to gravity is down, gm all over 2 t squared. And so it turns out that what we have to do in this problem, and this might have taken a little time to sort of get to, is what we need to do is we need to actually find the time it takes to get from here to here, and then we're going to use that information to find the range. So how do I solve this thing? I actually need the quadratic formula from Algebra 2 in high school. If it needs some dusting off, dust it off. But if I want to know the time, or if I want to know the zeros of this expression, t is equal to if I call this b, and I call this a, and I call this c, it's the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Okay, that may have been how you've solved it in your algebra class, but we're going to use that. So the opposite of b is minus root 2 over 2 v0 plus or minus square root b squared root 2 over 2 v0 squared minus 4ac. Well, since a is negative, it's plus 4h gm over 2 divided by 2 times a. Well, a is actually negative, and the 2 and the 1/2 cancel, so I get g Mars. Okay, and so this is the time it takes. So the time it takes, I'm going to, oops, I forgot my negative sign in there. So I'm going to distribute those minus signs because it tells us one important thing. So we get a positive root 2 over 2 v0 minus plus this thing, right? And I can square what's in there up. So root 2 squared is 2, 4 squared is 4, so I get v0 squared over 2 plus a 2 gm times h all over gm. Now here's the thing about this, okay? So this expression here, well, I need to know, I want the time that makes sense. So in these problems, you also have to think about, so when I have two solutions here, I want the correct solution. All right? And so it turns out that the positive solution gives me times a greater than 0, and the negative gives me times less than 0. And mathematically, that's just sort of where the parabola meets y is equal to 0 on the other side. So the negative sign solution gives me, if I were to backtrack in time, where that parabola hits the ground, but I want the positive value. So the time that I'm interested in is root 2 over 2 v0 plus square root v0 squared over 2 plus 2g Mars h all over gm. But we're not interested in the time, though. What we're interested in is the range, how far it goes. Okay. And so to do this, we have to recognize, again, that the acceleration in the x direction is 0, which means that my position is going to be the initial velocity in the x direction times time. Well, I know some of this stuff, right? I know that this is root 2 over 2, magnitude of v0, times time. And so when I plug this thing in here, when I plug the time in here, well, we can do it. It's not gonna be that enlightening, but root 2 over 2 v0 times this whole thing, root 2 over 2 v0 plus square root v0 squared over 2 plus 2 gm h all divided by gm, and that's close parentheses. Okay. So this relates the height of the volcano, the initial speed, is the initial speed at 45 degrees. That gives us our maximum range. And how far we go. And this expression is an algebraic expression that relates all of those variables. Okay? And you should play around with this. You should make sure that, it makes sense. That as v0 goes to 0, well, if the magnitude of the initial velocity is 0, it doesn't go anywhere. Okay? And as the height gets bigger and bigger and bigger, as h gets larger, the range gets larger, and that also makes sense. The other thing that you can do, and this is kind of cool, is you can think about what happens if I decrease gravity even more. So what if GM gets really, really small? Well, intuitively we would think that, well, probably the volcano would throw that rock quite a bit further. And it turns out that that's also right. That if you were to plug all this stuff in and think about it, if you would plug in some guesses for these numbers, you can see that as gravity goes down, the range increases.